This is Stochastic Processes, Module 8 Renewal Processes, Lecture 2 Generalized Renewal Processes and Renewal Limit Theorems. In the Lecture 1, we have discussed the renewal processes, definition and its properties. Followed by renewal process definition, we have discussed the renewal function, and then we have discussed the renewal equation, and also we have seen a few examples in the lecture 1. In the lecture 2, we are planning to discuss the reward renewal process. As a special case, we are going to discuss the Markov Reward models. Then we are going to discuss two different renewal processes, that is alternative renewal process and delayed renewal process. With this, we are completing the generalized renewal processes. The second half, we are going to discuss the central limit theorem, Longrun properties, and the three important renewal limit theorems. What is a reward renewal process? Let x1 be the time to the first renewal, and let xn be the time between n-1th renewal and nth renewal. The same definition which we have used for the renewal process. And also you assume that xi's are IID random variables with the CD of capital F of x. Since xi's are the inter-arrival times, the mean will be a positive. Mean exists and it will be positive. Let Rn be the nth reward at time t of the nth renewal. For each renewal, you are attaching the reward at the time of the renewal. Usually, Rn may depend on Xn. Now we are defining a new random variable R of t, function of t, that is nothing but the summation of Rn's, where n is running from 1 to n of t, where n of t is a renewal process. The collection of R of t for t greater than or equal to 0 will be called it as a reward renewal process. That R of t is nothing but a reward earned by time t. So from the renewal process, we are attaching the reward for each renewal, and by defining R of t is equal to summation of n is equal to 1 to n of t Rn, that will be called it as a reward renewal process. Note that unlike the xn, each Rn may take a negative values as well as the positive values. The xi's are nothing but the inter-arrival time of the renewals, whereas the rewards may take negative values as well as positive values. See the sample path of a reward renewal process. So the x-axis is the time, the y-axis is n of t, and these are all the time points in which the renewals takes place. The first renewal takes place, second renewal, and so on. So this is the inter-arrival time, and attaching the reward Ri to the each xn. And these Ri's may be negative or positive. Then the collection of Ri's with this form, Rt is equal to summation n is equal to 1 to n of t Rn, will be the reward renewal process. So it is very difficult to show the sample path of R of t. So here we are showing the sample path of renewal process with the rewards attached with the each exercise. Now we are moving into the simple example of reward renewal process. Consider an age replacement model. In this model, a component that is used continuously with replacements. Let x be the lifetime of the component, which is random with the distribution function f. The component is replaced by a new one upon failure or at a fixed time period capital T, whichever comes first. The replacement policy is called the age replacement because the component is replaced by a new one upon failure or at a fixed time period T. The cost of a new component is C1 and the additional cost is incurred by a failure is C2. Our interest is to find the long run average cost. Let NT be the number of replacements of components by time. N of t is a renewal process. Let R of t be the amount of cost incurred by time t. So this is a reward renewal process. So the long run average cost can be expressed as the ratio of expectation of R by expectation of X, that we are going to conclude later. Now we are using the long run average cost is the expectation of R divided by expectation of X. Expectation of R is nothing but expectation of cost during a cycle, and expectation of X is nothing but expectation of cycle length. Now one can find the expectation of cycle length, that is nothing but the expectation of the cycle length is a random variable which is nothing but the minimum of x or t. Here the component is replaces either upon a failure or at age capital T. Time between replacement is called a cycle, that is nothing but the integration 0 to t 1 minus f of x dx. Given that the reward or cost during the cycle R, therefore R will be C1 if x is greater than t. If it fails after t, if it fails before t, then there is additional cost C2, therefore the cost will be C1 plus C2 if failure occurs before the fixed time t. Hence the expected value, that is the expected cost, is either C1 with the probability x is greater than t or C2 plus C1 plus C2 with the probability x is less than or equal to t. So that is nothing but C1 plus C2 times f of t. Hence the long run average cost is nothing but expectation of R divided by expectation of x, that is nothing but expectation of cost during a cycle divided by expectation of cycle length. Substitute the values, you will get the long run average cost. Now we are moving into the special case of reward renewal process, that is a Markov reward model. A Markov reward model is a labeled continuous time Markov chain augmented with the state reward and impulse reward structures. The state reward structure is a function R that assigns to each state a reward R suffix S such that if t time units are spent in the state S, a reward of Rs times t is occurred. The rewards that are defined in the state reward structure can be interpreted in various ways. They can be recorded as the gain or benefit occurred by staying in some state, and they can also be regarded as the cost spent by staying in some state. And this type of Markov reward model is called rate based Markov reward model. The impulse reward structure, on the other hand, is a function of function tau that assigns to each transition from S to S dash, where S and S dash are belonging to the state space S, and the spending time in transition of S to S dash is positive, and the reward tau of S to S dash such that if the transition from S to S dash occurs, a reward of tau S of S comma S dash is occurred. Similar to the state reward structure, the impulse reward structure can be interpreted in various ways. An impulse reward can be considered as the cost of taking a transition or the gain that is occurred by taking the transition. Markov reward models are commonly used for the performance, dependability and performability analysis of computer and communication systems. In general, the reward rate is assigned on the basis of desired measures. Let z of t is nothing but r suffix xt be the instantaneous reward rate of the Markov reward model at time t, then the expected instantaneous reward rate at time t is given by expectation of z of t, that is nothing but summation of ri's pa of t. The expected reward rate in steady state is nothing but expectation of z is a summation of ri pi I. Suppose in the perform availability model, our interest is to find out the availability of the system, then one can assign the rewards for the up states are 1 and the rewards for the down states are zeros, then the expected reward rate will be the availability for the system by making a summation of ri's and the probability of being in those states. The different types of measures, namely steady state measures, transient measures, cumulative measures and performability measures, are supported by Markov reward models. For instance, steady state measures are computed from the steady state behavior of the Markov chain. So, for the availability model, if you know the steady state behavior of the Markov chain, such as a steady state probability of being in this system, then by assigning the rewards 1 to the up states and zeros to the down states, one can get the steady state availability of the system. Similarly, reverting the rewards, you can get the steady state unavailability of the system also. Under the assumption that the steady state distribution of xt, one can find the steady state measures by multiplying ri's with the pi i's, where I is I belonging to the state space S. Similarly, the cumulative measures denoted by y of t express the overall gain that is received from a system over some finite time interval. When transient measures are integrated over the time interval 0 to t, then y of t can be given as integration 0 to t r suffix xs of ds.